Hi there and welcome to this video for Senior Physics on Light and Waves. In this video we're going to explore wave types. Okay, so we've got basically two main wave types that we tend to explore. There are those waves which we classify as mechanical waves, and then there are those that are classified as electromagnetic. Now, a mechanical wave is basically where we get a wave that moves through a specific medium. For example, water, maybe something moves through air, and it has a sort of power, it has a mechanism. For example, if you look on the right hand side there, we've got ocean waves. They are what's known as a mechanical wave. When that hits you, you'll feel the energy of that wave passing through you. A string oscillating means going up and down. That has a mechanical effect. You can feel it as it goes through. Now the opposite is an electromagnetic wave. Now an electromagnetic wave also has energy, however it doesn't require the movement through a media. For example, sunlight. Sunlight, as we know, is an electromagnetic wave and it passes across space. Now space has no medium because it's a vacuum. Now on the right hand side there you can see a little diagram of the various types of electromagnetic waves we've got, going right from radio waves all the way through to gamma rays. Notice that at 10 to the 16, we've got the visible white light spectrum. Now we've already explored light, but light is an electromagnetic wave because it doesn't have to pass through any specific medium. So to recap, two main types of waves: mechanical, where you basically produce energy going through a medium, like dropping a stone into a river, you produce ripples, and the result is those ripples have energy. As well as that, you've got electromagnetic waves where they do not pass through any medium whatsoever, such as a vacuum. Okay, so when we look at our waves, especially when we're looking at our mechanical waves, we've got the idea of two main types. We've got longitudinal and transverse. Now, these can be utilized both in the mechanical form and the electromagnetic. Remember, light is thought to travel both in particles and also as a wave, and we'll explore that phenomenon later on. But yeah, we've got two main types, longitudinal and transverse. Now, longitudinal waves are exhibited in things like sound or seismic P waves. So when an earthquake happens, you get this pushing effect. Now, literally what happens is you get a push of the particles, so almost like a pulse. And we basically know that the speed of sound in air is approximately 330 meters per second, and in water it's 1500 meters per second. So depending on the density of the medium will determine how much of a push. Now, if you ever watch any Western movies, or for example, you often see the Red Indians putting their heads against the steel tracks, or people putting a knife into the ground and listening to the top of the knife. Now, what they're listening for is vibrations which are passing through the ground. Now, these are in the form of longitudinal waves. Now, remember, the ground has got quite a large density, high density, meaning the particles are close together. So what tends to happen is if you get any big vibration, the particles are going to bounce into each other and you get this pulse going through the ground and you can hear it. Try going and sitting at the bottom of the pool, especially if it's a noisy pool, you'll hear all the vibrations underneath. However, if you take the same sort of people and put them in a large open space like a field or an oval or what have you, the sound dissipates out because there's too much gap between the particles of the air and the energy is lost over time. Now, when we look at longitudinal waves, we can identify two main areas. We've got these ideas of compressions and rarefactions. Now, rarefactions are basically when it's the area behind the pulse of a wave. Now, you can see here with the yellow discs, the distance between the yellow disc is quite large, whereas we then get the compressions, which are the red discs. This is where the air particles are pushed together. Now, the particles will move with a certain speed, rather like having marbles bouncing into each other. What tends to happen is the rarefaction is the space between the marbles before they collide. When the marbles collide, then the result is we then get our compression. Now, another way of looking at this is through sound. Now, remember, all of the waves are going to be moving with a specific wave motion or wave speed. Now, if we take a speaker, for example, what a speaker does, it's a piece of paper which is linked to an electromagnet, and that electromagnet switches on and off. And what happens is the speaker pulses. Now, as it pulses, it pushes air particles. Now, as it pushes the air particles, it contracts them together. This is what we call the compression, and you can see that on the diagram where we've got those red air particles all compressed together. Now, obviously, when it pulls back, what's going to do, as it pulls back, the particles are going to become further apart, hence we get our rarefaction. The distance between each compression we determine as the wavelength. Now, what happens is those compressions and rarefactions are then picked up by your eardrum, converted into an electrical signal, and then your brain interprets that sound as a specific frequency, and obviously we hear whatever it is that we happen to be listening to. So that's longitudinal waves. Now, the opposite of longitudinal is transverse. Now, transverse basically produces the mathematical sine wave. And we can see an example here of the mathematical sine wave which is generated. Now, this wave can be utilized where if we're looking at ocean waves, it can be utilized. We can actually convert longitudinal waves into electrical waves, and we also see it on an oscilloscope often when we're looking at AC current. So AC current follows a sine wave. Mechanical waves such as wave motion produces a specific wave, and we can also look at it with respect to electromagnetic as well. Now, there's a number of points that we need to identify. First point we're going to identify is the peaks and the troughs. Basically, we get a top area, which is called a crest or a peak, and a bottom area, which we call a trough. It's just a way of identifying what part of the wave we happen to be looking at. So we've got crest at the top, we've got trough at the bottom. The next piece of information we can identify is the wavelength. Now, the wavelength basically is for one complete sine wave to be generated, and it's measured in meters. And it's given the Greek symbol lambda, which you can see there in green. Now, in this case, the wavelength can go from peak to peak, it can go from trough to trough, or it can go from midpoint to midpoint. So if you look at this diagram, you can see that there are two sine waves there, starting off on the x-axis, right at the point where the x crosses the y, and what happens is it goes up and down and back again. That's one wavelength. I do the same again, up and down and back to its original point. That's the second wavelength. Okay, so that is measured in meters. As well as the wavelength, we've got the amplitude given the symbol A. Amplitude is the point from the midpoint to the top of the crest or the bottom of the trough. Again, it's measured in meters. Okay, it's the size of the wave. Now, obviously, if you increase the size, you increase the amplitude. And that's the whole principle behind an amplifier. It allows the size of the wave to actually increase. As well as that, each wave will have a specific wave speed, and that wave speed will be determined based on the medium that it happens to be moved through. Through air, as I stated, it's around about 340 meters per second is the speed of sound in air. But obviously, waves can travel at different speeds. All you have to do is to look at a tsunami as it's moving through to hit the land, and it's got a specific wave speed. And we'll explore this idea of wave speed later on in the course. As well as this, we've also got the frequency. Now, the frequency is the number of waves that passes a specific point per second, and it's measured in the units hertz or Hz. Time period is the time that it is required for one wave to pass a specific point, and that's measured in seconds. So to recap, what can we distinguish from our transverse sine wave? Well, we know we've got crests and troughs. We've got a wavelength, which is the distance of the complete wave or one complete sine wave. We've got the amplitude, which is the size of the wave from the midpoint. Note that it's not the size of the wave from crest to trough. The size of the wave from midpoint to the crest or midpoint to the trough. Each wave has its specific speed, which we'll call V. It's got a frequency, which is the numbers of waves per second measured in hertz. And we've got time period, which is the time taken for one wave to pass a specific point. Now we can now use some of these terms and produce some mathematical equations. Now we know that any speed basically is categorized by the equation v equals distance over time. Now, when we're dealing with waves, the distance is classified with the term wavelength, or lambda, and the time is the time period, or t. So if we substitute these formulae, or these symbols, into the formulae, we then get that speed is the wavelength divided by the time period. Now, there is also a relationship between time period and frequency, and they're the reciprocals, or the inverse of each other. So basically we get t equals 1 over f, and f will equal 1 over t. So we can now substitute in for t 1 over f. So the result is that what we can do, we flip the equation. So what we then get is v will equal lambda times f. So to recap, we know that speed equals distance over time. We can substitute in lambda and t, or for the time period, so that we get speed of a wave is basically the wavelength times the time period. We know that time period is 1 over the frequency, or frequency is 1 over the time period, and by substituting in for t, we can also get an equation that speed is the wavelength times the frequency. Okay, so I hope you found that useful. I've put some exercises on this post that you can work through to practice some of those formulae. Okay, well I hope you've enjoyed this video on wave types. Join me again. Thanks for watching.